Good morning, everyone. I hope you can hear me. Please, someone confirm.
Yes, we can.
Yeah, okay. So we have still 4 more minutes to begin, so we can wait a little bit more for the rest. But of course, if you have any other questions, we can discuss it before the lecture begins. Okay, so the time is already 9:15, so we can begin. Firstly, I said that we will talk about the ROS, but that lecture will be on the next meeting because I realized that at the very beginning, when you start your project, you still need to know a little bit, think on your project on a little bit more general level. So not yet going into implementation into ROS, but thinking about the project as a whole and as a modules. Last time we were saying about the component-based design, which is saying of how to use, how to divide the problem to the smaller ones in this classical approach to divide and how to make it more simple to have smaller blocks that you can easier test, that because they are containing only most likely one or just a couple of functions, then you can more easily verify if they do what you want them to do. They have no or less side effects. And then there comes a issue of, okay, we have these blocks, we need to put them together, and we need to either, if you just use the ready blocks, we just need to know how to put them together. If we design the system, how to divide the system into these blocks. So let's say about the control architectures and the approaches that are used in this field. So firstly, what are the fundamentals of the architecture of robots? But of course, you can think about it not only in the case of robots, but in case of any other complex systems. Just the fields of division can be different. In robotics, we usually have the hardware, the electronics, and the software. In some other fields, the division may be different, but generally the architecture approach in other fields will be also useful. So firstly, when we say about the architecture, we need to think about two concepts. So firstly, of how to describe the structure of whole system. And it is an important, probably the most important issue, especially if you work in the project that is implemented by a group of people, by a team, because usually this division to the structure also needs a division that later on certain people work on certain parts of the project, but to have finally all the project to be able to work together, the system to work together, you need to at the final step you need to go to integration, and everyone who prepares the components needs to understand of what is the role of the component in whole system, so that the integrations work correctly. So as a structure, we say about two things. So how it is divided into subsystems, and that's quite clear, but also how subsystems interact. And that is really, really important, because usually when you just prepare a project by yourself, you can say, okay, now I have the output in that format, but maybe it will be easier for me to make an output from the program in another format. And if you work alone, it is not a problem. You just change it, and that's fine. But if on the other end, someone else uses the input, then you cannot simply change it. You need to inform and agree with the other side on the receiving side that what the change will be and what will be the consequences of the change. Maybe you heard also about some big failures caused by not properly defined interaction of the projects. For example, once one of the big projects in space industry was finished by a failure because it was prepared in a cooperation between continental Europe and Great Britain and US, and a team on one side of the channel they were thinking that the output is in metric units. On the other side, they thought that it is in imperial units. And a part of the rocket, the fuel tank was released too early, and all the rocket failed and just fall down to the earth, just because the interaction was not completely agreed and the units of the numerical values were not agreed between the teams. So you need to do that, but remember not only to do it at the beginning. Of course, it would be nice if you can just define it at the very beginning and not change it, but the practice is that you usually need to change it. And then when you change it, you need to remember about the other side of the system. And if you will be working in ROS in the systems of that, using the approach of publishing, subscribing, which becomes more and more popular, it usually means that the connections are not one-to-one, but many-to-many. So if you change the format of the output, on the other end is maybe not only one block, but multiple blocks. So you may not need to agree only with one side, but with multiple sides. Okay, then how to represent the structure. And in fact, the main two approaches are either you use the formal approach, so UML, or you can also use the specialized version, which is a SysML from System Modeling Language, which is like an UML with some specific notations. I'm not sure if you ever heard about or ever tried UML as a description. Okay, if not, what we need to say is, okay, UML is not one type of the graphs. In fact, UML defines several, I think 7 or 8 different perspectives at which you can look. So like a class diagram for object-oriented programming, sequence diagrams for time-related issues, and so on. And each diagram has specified certain standards of representing information within these diagrams. And why it is used? It is used mainly for that reason that if you have something standard, if people from different companies, from different fields want to communicate correctly, they need to speak the same language. And this is like kind of the language to represent your idea of the system and how the system operates. As I said, UML defines own elements of the diagrams that are, it was defined in computer science, so mostly dedicated for the programming. Later on, there was added the SysML, some additional diagrams and some additional type of blocks in these diagrams to represent not only software, but also hardware and software connected components. But this UML approach is useful, especially if you work with in big teams between different companies, for example, to communicate between the client that orders some systems and the company that prepares it. But very often, and in most cases, you just do it informally, just to present certain ideas within the team. And of course, those informal representations can be very different. They can either be inspired by UML or can be just their own ideas. Okay, so that's all about structures, about the style. Firstly, what you show in this in the different diagrams representing architectures. So, firstly, it should present certain concepts that you want to show on the certain diagrams, and it also uses some combinations of various elements. It is also possible and quite common that in fact you don't represent all the architecture with one single diagram. Usually you present different elements of the or different perspectives of the system on the on different of different diagrams. So you can have, for example, like a chart of communication, a chart of package connections, and especially when you do it in informally, you can simply mix different approaches in a way that is useful for certain teams. And just to show the idea, not to talk only about the theory, I will show you the part of the paper we were talking last time about the remedy system, and you can see the an example of the architectural diagram representing the main component blocks and the communication between them. If someone wants to go into details, you can find it in the notes also on the portal. But what we do have, of course, it is completely informal. You can see the hardware elements that are connected. So it is just a nice picture. So it's mostly for good-looking elements. What you can also see, firstly, the location of that part. So you have some assistant panel, and you have mobile platform, and you can see that, okay, so everything, almost everything except of this one block is on a mobile platform. And then you have like hardware, Orocos. Orocos is a real-time system that works that was operating the low-layer hardware of the control of the remedy platform. And then you have the ROS. So these blocks were implemented in Orocos. These blocks were modules of ROS. Then you can find the name of the blocks, and then you can find the flow of the information. So you can see, okay, someone has a control path. The data from the path goes to the path teleoperation, whatever it is. It was just a name of the ROS package. This block generates the velocity, and the velocity goes to the multiplexer. Then you have some navigation module that also generates the velocity. It goes somewhere here. So someone looking at this diagram can say, okay, so firstly, what components are used in the system, which component communicates with which one. So you know that when you, for example, want to change the let's say this control logic, so you know that it influences on the output side the multiplexer of velocities and navigation, and also the assistant panel. So you know which with authors of which blocks you need to contact, or which blocks you need to check if you want to change anything in this block. Of course, it doesn't provide all the information, so it gives you some information of what is passed between the blocks. In fact, on the ROS side, those are the names of the ROS topics, the types of the ROS topics. So we will tell about it next time. But it is the type of the data that goes. But for example, it doesn't show the names of the topics that also needs to be agreed at certain point, and it's not visible in that part. Okay, so that's a description of what are the blocks, what is the data flow, and what are the hardware components in the system. Later on, you can see another diagram that is a lower level diagram that describes only one of the blocks, but it goes to the hardware level, because it shows, okay, we have the DC motor here with the encoder and the switch. We can have this block as a DC driver that is connected to certain timers of the microcontrollers, and then when you implement it, you can in an exact implementation of this wheel driver, you know in your program, for example, which timer you have reserved for the first motor, which is reserved for the second motors. So that's this lower level part of the architecture. So you can see different types, different schemes, and different informations on each of the graphs. Okay, so let's return back to this data. So what is this architecture for? It's mainly used to communicate your ideas to the other team members or the other users or people that are engaged in the project. That's why you usually limit the information to this that is necessary to show the certain perspective, and also you want to make it relatively clear. So that's why if all teams, everyone works in UML, you usually go for UML. If you want to show it to someone who is not familiar with UML notations, maybe you can present in other style. Just the main point is to be clear and consistent in what you say, what you present. Okay, so what we can present on these different layers of the architecture. So firstly, asynchronous interactions. For example, in ROS, when you most of the communication in ROS happens asynchronously. So that what you have seen on this remedy example, it was the asynchronous communication between the blocks. Then you can also present some real-time requirements. So if your system has certain deadlines or certain frequencies that needs to be met for certain communication channels, you can also indicate it on the timed interaction diagrams. You can also use information about uncertainty, and you can also present various temporal scopes. So the things that needs to happen, as I said, we can have the real-time part of the system. We can have the not real-time, but still time-critical components. So the things that need to happen quickly. And you can also present the elements that are not having any special time requirements. So you can have, okay, some elements of the user interface may be not important or maybe not critical for the system. You can say, okay, so for example, saving the state of the system or saving the data maybe it's not important how quickly it will happen, but for example, you want that when the user has the remote safety stop, you define that, okay, this element is important for the safety of the system, and we need to stop the robot within, for example, 100 milliseconds. So that's the time critical movement. So those also, it is the time you can either show in different perspectives on the graphs, or you can just present these time restrictions on certain graphs. Again, with synchronous and asynchronous interactions, they will usually they can either be shown on the communication graphs, as we've seen before, but you can also use a kind of UML sequence graph to present of how the communication is done, especially if your communication protocol requires a few multi-step interaction. So so for example, one subsystem needs to send some data to, for example, to start measurement, wait for the response, then wait for the when the measurements are completed, and after they are completed, it needs to get back the data. So that's a way what you can present also in a special type of the graphs. When you use another example is when you use like a radio, especially and not synchronous, like you can use, for example, LoRa. You need to have all the complex procedure of scheduling the data that you want to request, and when wait until you receive the response, or if you don't receive, you need to know of what to do. If you replay the request, or if you change it, or what may happen in all these situations. So it's good to know, think about it in advance, and have it ready. And as I said, it's kind of the must if you have a bigger team and you want everyone to understand of what's going on. But even if you do it by yourself, it's good to have it somehow illustrated and remember it when you prepare the implementations. Just to have it in your mind and have it as a reference. Of course, I would also like you to think about having this kind of the approach used in your project. So especially those projects which are a little bit more complex, having more than one part, more than one component, you can think of how to represent the architecture of your solution in that way. I hope you will see then that it can be really useful and well explaining your ideas to someone who will see it and who will try to understand of what you are doing. Okay. Okay, I missed this point, which is a reliability. Okay, that's also another requirement that can be included. So if the data is critical or if it's not. Okay. So that's about representations and importance of the architecture. Now the question of how the architecture can be organized and how the blocks can work together. And there are different types of the hierarchy of the components that may happen. So you can have a centralized architecture, and the centralized architecture was something that you usually go for, especially for smaller systems. It generally means that you have a central processing unit. So there is some, oh, sorry, that there is some CPU in there, and everything in the around is just connected to this central unit. So all the sensors, all the effector go to the same central processing unit, just a single one. As I say, when you start with the smaller system, it's a natural way to go. But if the systems get more complicated, you probably will need to divide and separate certain tasks to some other controllers. So then it happens that you have a central CPU or main CPU, then you have some components, maybe smaller units that process certain data in there. Of course, you can also have direct connections to the higher level, but at least some part of the calculation, some part of the process is done on the lower level, and the transform data are included, are presented to the higher level that, for example, makes the decision. Looking at the projects that you already presented on seminars, some of you already go in this hierarchical approach directly from the idea. So for example, you can have the PC computer that does most of the calculations, but then you connect the microcontroller that does some, for example, like PID control of the robot, and maybe even on the lower level you have this the direct control of the motors with even smaller microcontrollers. Some of you also go with not directly. For example, if someone uses real-sense camera, so the teams that use the real-sense camera, in fact, the processing of the data from the real-sense is already done on the microcontroller that is inside the camera. So you don't get direct data from the camera in the sense of getting it from the small sensor, but you get the data that is already processed, calculated in another form, and then you process it by yourself. So this calculations is already done separately, and they can be these completely distributed systems. So without a central unit, we have a block that does one part, at the same level of importance a block that does the other, and then we have some elements connected to one, some connected to the other. So and of course they can be not only two, they can be multi of such elements, and each of them working out own decisions, but they can also communicate with each other. What we can also say about this hierarchy. Okay, this hierarchy can be organized both on the hardware layer, and then it is clearly visible. That's the example that we are saying here. So that's CPU and microcontrollers, or separate CPUs. But they can also be done on only on a software layer. So in that sense, that you write a main program that uses the data of some sub-programs, but these sub-programs are run also on the same computer. That approach you will probably use in ROS. So you will have your main program, but you will already use the processing from the other components that maybe you will not even write by yourself, but you will take just ready components that make some part of the calculations, and you just integrate it in your system. So this centralized or hierarchical approach can be also realized in the same computer, but only on a software level. So you have the main program, but the program does not directly process all the raw data, but it uses already data pre-processed by other programs. Okay, what about the differences? Of course, the centralized systems has the highest influence of what is going on with all the data that you have. But when the system gets more and more complex, this interdependence of data and the fact that you need to deal with all the possible things for everything what can happen with this data. So some data may arrive, they can be, some they may be lost, some may be erroneous. You need to deal with everything in a single unit. Then with when the system gets to a certain level of complexity, it's hard to deal with it in your single computer or in your single program. That's why came this division. So we make a division. In fact, you can think about this component-based approach. It's like, okay, it's a realization of this hierarchical or distributed system. So in the way that you separate certain tasks to the either subcomponent in the hierarchical distributions, or you just separate one task to another part of the system on this distributed level, then of course you lose certain information because you only get the process data, and you need to trust that the component calculates it correctly and returns every information that you need. But of course, the system at the higher level or one of the system becomes more simple, and it's easier to, again, it's easier to especially test and validate it, because you probably already know with your experience with programming that that the testing and debugging of the program can use most of the time of working on the system. So you usually the thinking about the system and first implementations take much less than making the system running correctly and removing all the errors. So that's what we try to do going in the hierarchical or distributed systems. Each of the components should be less complicated, so easier to validate and to make it working correctly. Okay, so now the question is, okay, when we have the hierarchical system, how we divide it? So we can divide it, for example, in temporal way. So at the lowest level, we do everything that needs the real-time approach. So with the short deadlines. Then we have the elements that have that should happen quickly, but without these requirements of the real time. And then at the highest level, we can have the event-based. So the elements that happen asynchronously, and we are just waiting for the signal that something happened, and then we pass to another part of the behavior. So these event-based systems, I don't know if you had any more experience with it. One of the standard example of the event-based system is the user interface. And for real-time system is like a motor controller. Controller, you need to send information how the to not make it stop. If you send the PWM signal, you need to you have set exactly defined time steps when you need to send, okay, when the signals go up and when it goes down, and you need to do it with the very high precision up to the milliseconds or sometimes even microseconds. Uh, but on event-based system, it's like things happen with their own pace, and you cannot even predict of when it happens. So the user interface is such a good example because you never know where the user clicks anything on the user interface, and and you are just waiting until something happens, and then you may and probably wait again. In the robot systems, one of the approaches like executing the movement command. This when you for the robot to move to a certain location, and of course there happens something at the lower layer. Some motors are being moved, some encoders are measuring. But on the higher level, on the event-based system, you are just waiting until you get the signal that, okay, signal position, and we are ready to do the next line of the program. So this temporal division. Then you can have the task-based division. So you can have, for example, a task of navigation, and you can separate it for planning the path, and then executing the motion, measurement, and creating the map. And those will be the task-based modules of the program. And of course, they can be also kind of the natural dependent on space. So you can divide the components based on where they are physically located. Components, they are on the microcontroller, they are on the main computer, maybe on the user panel where you present the data, or some components inside the website-based interface. So that's another approach to the division. And yeah, those are just the ideas, and it's not like that any of this approach is better or worse. It's just it always depends on the situations, on your project, or on what is needed in your certain with your certain requirements. So that's the in fact that's the moment where your engineering task appears. Okay, you know the options, and then you need to decide of what will be the best for your use case, for your project that you are now doing. Okay, again, one of the examples, the three-layer architecture divided in the temporal way was kind of is in fact kind of the standard that that you can find in many robots. So you have the lowest layer, this green part, which is related with this real-time and direct connections to the hardware. So that's the example of the Flash robot that was done some time ago here. And it was kind of a social robot that was just moving around, was able to look at people, talk to people, understand some commands, and so on. So you have all this hardware moving the head, moving, observing, recording the speech and speaking also. So all these hardware are related part, and that having own simple drivers. Then on the middle layer, you had a certain functions that were connecting the highest layer with the lowest one. So these were like certain functions like play certain music, or speak, or recognizing certain separated kind of the recorded speech. In movement, it was like, okay, blink at eye. And you can imagine that blinking an eye is like moving several motors of to make this action to happen. Yeah, so these middle layer components were just simple functions that were usually utilizing more than one components from the lower layer. And then they were the highest level that were the usually the event-based components or event-based functions. For example, like follow a person, which was engaging both the observation part and also the movement. And this following was including observing where the person is, sending the command of the movement, but also dealing with the situations when the person disappeared and some reactions of any failures. So that's the approach of the three-layer architecture which is temporal based on the time. So as we said, they were different realization of the architecture with different interdependence between the components within them. So one more thing. On this three layer, you can see it's as well, because you have a mind that controls different middle layer components, then each component controls some low layer components. What you can also, they are not usually not interchanging. So the motor are only influenced by this part of the middle layer and not the others. So it's the middle part of the system had only own separate subset of the lower layer components and physical elements that were associated with it. Okay, so think about this division of the architecture. We can say that the approach to whole control can be done in one of the three or four main approaches. So first one is the deliberative approach. And this deliberative approach is the one that the robots started with, and that they are still used in industrial robots. And it's called the deliberative or sense plan act. It means that in this approach to the control, it can be done either on the, you can think about this deliberative approach both on the lower level of the component. Of course, it's not the lowest one when you have just the interaction of with the single elements, but any block that is associating several sources of data and combines different elements together can be done in one of the ways that we are saying, we'll be saying now. So the deliberative or reactive or behavioral and so on. So deliberative, this sense plan act means that every processing happens in a serial way. So we collect the data from the sensor. We have this perception phase. then we have the modeling, which usually means transforming the data from the sensors to the useful information for us. So, for example, we have the laser scanner. We are walking around, looking around with the scanner. At the perception level, we just get a list of distance measurements uh, and the angles at which we have measured something. So we know, okay, at 0 degree, we have 3 meters, at 10 degree, we have 4 meters, and so on. So that's the perception. Of course, it's not an information that is usually directly useful for us. We need to transform it, and it is done in this modeling phase. We need to transform it into the information that we want to use. So, for example, you may want to know what is the safe space in front of the robot. So you just analyze the angles and the distances and say, okay, we have like 3 meters of the free space in front of the robot that we can freely go. That's like a simple modeling of the environment. You can make it a little bit more complex. You can say, okay, so let's make let's mark the obstacles around the robot and know where the obstacles are based on the data from the laser. Later on, this modeling can be even more complex, and you can say, okay, let's try to recognize what kind of the obstacles are. Is it a table or a chair or maybe a wall? So this modeling can also be more complex. Anyway, when you have the model of the environment, so the information that is in the form that is useful for the next task, you usually do the planning. Yes. So if you were only if you only wanted to go without collision somewhere, you may just use the information about the free space, and you can use it, plan the path to go, and simply be ready with that plan. But if you have a more complex robot and you say, okay, the task for the robot is to pick a bottle of water from the table. So, okay, now you need to know where is the table, where is the bottle. You need to know how to recognize them. So then it goes for the planning phase. Of course, if you have the plan, you start to execute it. So divide the execution of the plan, for example, a path that you want to go forward 1 meter and then rotate 30 degrees. You need to transform it to the motor control and saying, okay, so if we want to go forward, we just need to give that angular velocity for both wheels the same, and then it goes as a power or PWM signal to the motors. So we start from the beginning and make all the process in the serial way. Okay, so what is good and what is bad in this approach? A difficulty that lies in this approach is that these elements, especially planning, is computationally complex. And what we need to remember that all the process, so having this whole process, especially planning and modeling, that can take quite a lot of time. The reaction of your system, so the time between the motor response to the signal from the sensor can become quite long. So this is the disadvantage. Of course, there's a main advantage of the system. So you can do a strategic planning and optimization. So if you know everything at the beginning and you process all the data, so you can also think about the optimal plan for your robot, and you can also plan ahead of what's going on. So good for optimization, good for strategic planning, not so good in the sense of the time that is needed to execute all the plan. As I said, that's how the robot started. That's how the industrial robots were working, because you usually need the optimization. It's also the time delays are not so critical there, because usually, especially when this approach was used, the industrial robots were used on high volume productions when the tasks were very repeatable. So you could optimize the task once and then run it hundreds or thousands of times, producing the same elements. So this optimization was not done in real time, it was done in advance and then only repeated. So it could be used in that way. But at a certain moment, it appeared that some people started to think, okay, but when you need to react quickly to the certain events, this approach will not work quickly enough. Moreover, some biologically inspired roboticists, they say, okay, but the humans or animals or some simple organisms, they don't have big brains, and they do not think about everything what they do. Sometimes they simply react to what happens without thinking. So we have in human case we have some reactions that do not involve the action on the brain. They just use the spine response. So then they came to the idea of the reactive approach. So in reactive approach, the data from sensors are influencing directly the effectors. Okay, so that's some error here. So the reactive, okay, I'm sorry, to correct. So the drawing of it should be like that. So we have the sensors. Here we have the actuators. And each of the blocks works separately. So we have like second block, third block, and we are just influencing this block independently. So we can have like, okay, collision avoidance block that just gets the data from the sensors and moves to the actuator. Then we have the map creating blocks, does something and sends some data to the actuators. Of course, that was kind of the original raw idea. Then someone realized, okay, but if we have many different signals going to the actuators, we really cannot, they can be contradicting to each other. So one block may want the robot to go left, another wants to go right, and what will happen with the robot? So later they modified it, adding a kind of the arbiter. So that was the arbiter that was saying which one of the blocks is currently ruling the robot and sending a single signal to the actuators. Okay, so what one need to remember is that this reactive approach was more or less an interesting idea, biologically operated, but not inspired, but not really practically useful uh, in many in many practical solutions, because you could not really predict of what this kind of the robot can do. So in fact, it was more like an experiment than the real useful system. But then there comes the system that was a hybrid system, and that the hybrid system is the one that is presented on the drawing that appeared here for a while. So the hybrid system was the system that has a deliberative part that uses all the planning, and that has the reactive part that just has a simple reactions. And then these subsystems communicate with each other, and also they use the coordinator before going to actuators. And this kind of the hybrid, so it should be like hybrid. So the hybrid system is in fact used in many robots where this reactive part is responsible for the safety. So usually this reactive part is like simple collisions avoidance, or even simpler stopping the robot in case of detecting any any conditions that is unexpected or maybe dangerous, either for human around the robot or for the robot itself. So, for example, measuring the systems, we have the safety laser scanners. If something appears closer than a predefined distance, the robot can stop all the motors and cut off. In fact, it's like cutting off the power from the motors. We can also can use bumpers that can also stop the robot, and so on. So this reactive part is really present in many systems, but quite often limited to the safety conditions. So sending just, and as I say, in most cases, it doesn't even send any other movement commands. It simply switches off the movement of the motors, or cuts off the power. Okay, and going forward. So that was the reactive systems. So the summary of this reactive systems is that it really doesn't, because of not having complex models and not having complex algorithms. That's why it was not really useful in any practical robots. But the advantages of it were that it was fast. It could work in unknown environments. So because you don't know what to expect, the planning, deliberative planning, is not really working well, because if most of the things that happen are unexpected, so you cannot include them in your plan. Okay, and disadvantages: no storing informations, no optimization, or no complex behaviors. And what was the okay, but anyway, despite of not being useful in the real systems, it gave certain ideas of creating the systems together. So one of the idea was those hybrid systems, putting two layers and combining them together. Another approach is the behavior-based. And this behavior-based is a kind of the upgraded reactive system. In fact, it's very similar to what we already said of what this component-based approach and what is a natural in ROS. So those things are in fact quite well tied together. And what is behavior? So behavior can be thought as just a simple component, the component that has certain activation conditions. So the component can be inactive in most cases, but if something happens, the component gets activated. And this component has certain inputs that is called the stimuli. As we said, this kind of the robotics is biologically inspired, so it also uses the terms not from automations that we are used to, but from the biology. So they use stimuli as an input. The output they call the action and the process itself. So each of these behavior-based blocks realize certain behavior. It can be complex, so not as in pure reactive systems. It is not very simple. It may contain memory. It can contain data also coming from other blocks. And in fact, it is something that can be easily implemented as the components within ROS system. And this behavior-based approach, they can be also interconnected. So they can the data. They may not only be connected to the sensing directly and giving the action, but quite often they can be the output from, for example, like action from the block 1 can go as an input to block 3, and so on. So it can create all in a different way interconnected blocks, and in fact in that way you can implement all types of the structures that you can imagine. In fact, so they can be used. You can all do it either more reactive, either more deliberative, or really create a complex network not similar to any of those previous approaches. So what we can say about this? So firstly, each of the behavior should be similar to the components. In fact, it should be task or responsibility based. So they should do something, some useful piece of work. They create a network, as you could see with the way it's connection. What is this relatively simple? Okay, it is in the sense it's simpler than the single processing block that we can have in deliberative approach. What else? They can incrementally. So you can think of, okay, you already have a system, and if you want to add an additional function to it, you just put another block, connect the inputs, connect the output, and it's already working in the system. It was not possible in the deliberative approach, because if you wanted to add some additional function, you usually need to rewrite all the main program, because the main program was doing everything. What is also important that they are executed in parallel. So each behavior is independent from each other. So it doesn't wait for the output of another or processing of another to be finished. It just does its computations at the same time. So therefore, the execution of these behavior-based systems is simply faster. Okay, so what are the other features? They may store complex information, something that was not possible in the reactive systems. Therefore, they are more powerful, and they can also exploit interactions between the modules, what was not possible in other approaches. Okay, that was this hybrid we already talked about. And in reactive, so the reactive can where these kind of applications can be architectures can be applied. Reactive in environments which require immediate actions, environments that are highly changing, dynamic, but you don't expect the system to learn or to predict of what's going on. Deliberative, everywhere where you need the full optimization and strategy development. But because of the complexity, they are used in static environments or very limited variability. So that's why they are used in industrial environments. Usually, you know what may happen within this area. You have the robots isolated, so there is a robot, there is maybe some other machines, but you know what they are doing and what they are. You know the produced elements, produced pieces, and nothing else not may happen. So the variability then is limited. And it's not only small, but it's also predictable. So you know what may happen. And all the unpredictable things usually stop the robot. So if a person enters close to the robot, the typical industrial robots, all the production manufacturing cells should be stopped, yes, and wait until we return to the normal predictable state. Hybrid systems for environments that require a big amount of planning, but also small set of actions that are independent and executed quickly. As we said, the most typical approach is that almost everything is done in the deliberative part, but the safety is ensured by the reactive part of the hybrid system. And the behavioral for the environments that are variable and require quick response and adaptation. So requires some planning, but it is possible that this planning is not optimal and the strategy is not optimal, so you have some place for the errors. Okay, so maybe some questions of what kind of architectures would you select for? Let's make a quick some ideas of, for example, if you have a search drone that looks for a castaway, which kind of the approach would you use? So which one of the approach? Which one, reactive or behavioral? Okay, okay, reactive. That would require some. Okay. environment is changing, yes. What can be a problem with reactive approach is because it doesn't really have a big memory. So if you want to search a big area, you may not remember whether you have been there or not. So the planning may be not optimal. But behavioral, it would be a better approach. Of course, one need to define again, the architecture itself will not really solve the problem by itself. Yes, so you can do a good or bad behavioral system. You can do good or bad deliberative system in each case. So the architecture can only help in achieving the goals, but it will not solve the problem by itself. So behavioral system will probably work, but of course it will depend on the behaviors that are selected and they are implemented. In fact, in the first approach, almost everything could work well. It's just the different properties of the final systems we could expect. And in fact, in other selections, it's not a single correct answer. It's always of what you, after your selections, you can expect certain properties of the system that you created, or maybe certain different problems to be solved when designing and implementing the system. But in most of these cases, all of them can be used. Of course, maybe in factory AGV, you will not use the only reactive systems because you want this robot to know where it goes. But all the other three approach could be fine with it. The same with the castaway search. When we look at, for example, the Roomba robot that is cleaning, so or let's say vacuum cleaner robots. So there are some robots that can plan their path. They do a mapping of the room, and then they just clean it in a certain order. But the Roomba that started and was quite successful was based on the random walk. Yes, so it was just going forward until hitting a wall, and then rotating in a random directions and going there until hitting a wall again. Okay, this was one of the behaviors, but also switching between the behaviors was partially random. So there was like this random walk through the room, then was following a wall for a certain time that could also be random. So yeah, you can do it in a reactive way in that sense. You can do it in the full planning way, and the system will work, but it will work differently. So that's something that maybe as a final message from this, that it's not it's usually not a single good solution. Usually you need to select one of them, and most of the cases different solutions will solve your problem. The question is of the resulting properties of the final robot, and the difficulty of the process of implementations and different problems that you meet on the way of implementations. Okay, so think about it, especially about the last questions. I will not ask you aloud now, but you can also think of how what approach you use in your project, then which one will be the best for you in these particular situations of what you have. And as I looked at the projects, at least as presented on seminars, yeah, they will be different approaches are possible, and it's not, again, not a single solution for any of them is the only correct one. You can make your choices. Okay, so that will be the end for today. And maybe you have some questions. We have some time to answer them. Okay, so if there are no more questions, so thank you for your attention, and yeah, and we meet with some of you today on the project, and to the others, I may say goodbye.
Thank you. Goodbye.